Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Hello and welcome back to our exploration of the fascinating world of science and discovery. It is Tuesday, February 17th, 2026. And today, we're pointing our attention upward, way up.
We are indeed. We're looking at our nearest neighbor, the celestial body that has captivated humanity since we first, looked up at the night sky.
The moon. It's the ultimate constant, right? You look up at night, and there it is. Sometimes it's a sliver, sometimes it's a big, bright orb, but it's always there. It's comforting, it's reliable. Mm-hmm. And I think if you ask the average person on the street, or even me, honestly, before reading this material, to describe the moon's geology, they'd probably say it's a done deal.
A fossil. That's the word that's often used in textbooks. A planetary fossil.
Exactly. A big, silent gray rock where nothing has really happened since the dinosaurs were wiped out. Maybe even longer. You see the craters, the dark spots, and you figure, okay, that's the furniture. It hasn't been rearranged in billions of years.
It feels static, unchanging.
It does. But the source material we are unpacking today is going to dismantle that idea pretty thoroughly. It turns out that dead is a very relative term in planetary science.
It absolutely is. And this new study really drives that point home. We're learning that our quiet neighbor is, well, not so quiet.
Not at all. We have a fascinating new study here, published in the Planetary Science Journal, coming from a team at the National Air and Space Museum Center for Earth and Planetary Studies. And the headline is not just that the moon is active, is that the moon is actively shrinking.
And shaking. Don't forget the shaking.
Right. It's getting smaller, and it's trembling while it's doing it. So our mission for this discussion is to unpack this incredible global map and analysis produced by these scientists. We're going to talk about a specific geological feature called small mare ridges, or SMRs for short.
SMRs, yep.
And we're going to figure out why the moon is wrinkling up like a raisin, and more importantly, what that actually means for the humans we are planning to send back there.
Because it really changes the risk profile. It changes it significantly for future explorers.
So let's start with the discovery itself. The study centers on these small mare ridges. I love a good acronym, so we're calling them SMRs. But before we get into the numbers, help me visualize this. If I'm an astronaut standing on the moon looking at an SMR, what am I actually seeing?
Okay, so to visualize this, you have to understand the landscape first. The moon basically has two types of terrain, very broadly speaking. You have the highlands.
The bright parts.
The bright parts, exactly. They're rugged, heavily cratered, mountainous areas. Think of the man in the moon's face, the light parts. This is the ancient original crust of the moon.
Okay, the rugged white parts. Got it.
And then you have the marea.
The seas, from the Latin.
Marea is Latin for seas, yes. These are the dark, flat plains that make up the other features of the man in the moon. Ancient astronomers, looking through early telescopes, thought they were actual bodies of water because they looked so smooth compared to the mountains.
But they're not water.
No, not at all. We know now they are vast solidified lava flows, mostly basalt, very dark rock.
Okay, so I'm standing in the middle of a basalt plain. It's dark, it's flat, it's covered in that fine dust. It's supposed to be the flattest, smoothest part of the moon, right? The easy place to land.
That's been the assumption, yes. For a long time, we thought it was relatively featureless, barring the occasional impact crater. But this study, led by Cole Nikever and Tom Waters, has produced the first global map of these SMRs.
And what would it look like?
If you were standing there, you wouldn't see a giant mountain range like the Rockies. You'd see a ridge, a wrinkle in the ground.
How big are we talking? Is it like a speed bump?
Yeah.
Or more like a hill?
Bigger than a speed bump. They're small in planetary terms. That's why they have that name. But they would be pretty substantial if you're trying to hike over one. We're talking about scarps, which are cliffs or steep slopes that might rise tens of meters high.
Tens of meters, so like a multi-story building.
Exactly. And they're not just little mounds. They can extend for kilometers, winding across the landscape.
It's like a long winding wall or a buckle in the pavement, just on a massive scale.
That's a great way to think of it. A buckle in the lunar pavement. But what makes this study such a breakthrough isn't just identifying one or two of these. I mean, we've seen oddities before. It's the sheer volume, the number of them.
I was looking at the data table in the report, and the numbers are just startling. They identified 11,114 new SMR segments.
Just on the near side lunar Maria, the side that faces us.
That's over 1,000 geological features that we hadn't cataloged them before?
We hadn't mapped them systematically. We didn't understand how widespread they were. And when you add these new findings to what was already suspected or known in isolation, the total count of these small mare ridges across the moon jumps to 2,634.
2,600. That is a significant amount of wrinkling. That's not just a localized anomaly, that's a pattern.
It completely changes the map. It strongly suggests a global process is at work.
I have to pause on that for a second, though. I mean, we've been staring at the moon with high-powered telescopes for centuries. We've sent orbiters. We've literally had boots on the ground. Apollo astronauts walked on the Mare. How on earth did we miss over 1,000 of these ridges?
It's a combination of a few things: resolution, lighting, and, frankly, attention. We knew about similar ridges in the highlands. We'll get to those later. They're called lobate scarps.
Right.
But the prevailing assumption was that the Maria, those deep, thick lava plains, were structurally different. Maybe thicker, more stable, less prone to breaking.
So we weren't really looking for them there.
We weren't looking for them on this scale. Finding them widespread in the Maria is the game changer. Cole Nypaver, the lead author, he emphasized this. He noted that this is the first time scientists have documented the widespread prevalence of these features throughout the lunar mare.
So it's not that they were invisible. It's that we didn't realize they were everywhere, that it was a consistent pattern.
Precisely. It's like looking at a smooth sheet of ice on a lake. From a distance, it looks perfect. But if you get down on your hands and knees with a magnifying glass, or if you catch the light just right at sunset...
The lighting.
The lighting is key. Low-angle sunlight makes shadows that reveal subtle topography. You suddenly realize the whole sheet of ice is crisscrossed with tiny stress fractures and ridges.
And those fractures tell you the ice is under pressure.
Exactly. They tell you the ice is moving or changing shape, that it's not as stable as it looks.
Which leads us perfectly to the mechanism, the why. We have 2,634 of these ridges. The moon is wrinkling. So why? I thought the moon was a solid frozen block of stone.
To understand the why, we have to do a little comparative planetology. It really helps to look at Earth versus the moon.
Okay. Earth versus moon. Ding, ding. Fight.
Chuckles. It's less of a fight and more of a contrast in styles.
Yeah.
Earth is driven by plate tectonics. We all learned about this in school. Our crust is broken into these massive puzzle pieces, the tectonic plates.
Right, the North American plate, Pacific plate, and so on.
And they float on the semi-molten mantle. They crash into each other to create the Himalayas. They pull apart to create the Atlantic Ocean. They slide past each other to create the San Andreas Fault. It's a chaotic, multi-piece system.
They're very dynamic.
Everything is constantly moving and recycling. It's a very active surface.
Right. A dynamic puzzle where the pieces are always shuffling around.
The moon is different. The moon is what we call a one-plate body.
One plate, so it's just a continuous solid shell.
It's a single solid lithosphere. There are no other plates to crash into. It's like an orange peel that hasn't been sectioned yet. Just one solid piece.
So if there are no plates colliding, how do you get a ridge? How do you get a mountain? Usually a mountain is formed when two things smash together, right?
Right?
Like cars in a head-on collision, the hoods just buckle up.
On Earth, yes. That's the primary mountain building process. But on the moon, the ridges are formed because the moon is shrinking.
Shrinking. It is getting physically smaller, the whole thing.
The whole thing is contracting, yes. Its radius is slowly but measurably decreasing.
Okay, help me with the physics here. Is it evaporating? Is it leaking mass into space or something?
It's a much simpler process, actually. It's thermal contraction. You have to remember, the moon was born in incredible violence. The leading theory is the giant impact hypothesis.
The big whack.
The big whack, exactly. A Mars-sized object smashed into the early Earth, and the debris from that collision eventually coalesced to form the moon.
So it started out hot, very hot.
It started out molten, a global magma ocean. And for the last 4.5 billion years, it has been slowly radiating all that primordial heat out into the cold vacuum of space.
It's cooling down.
It's cooling down. And as we know from basic physics, when most things cool down, they contract. They lose volume, and the atoms and molecules get closer together.
So the hot interior is cooling and shriveling up like a balloon losing air.
That's a good way to put it. But the crust, the outer shell, is hard rock. It's brittle. It cooled and hardened a long, long time ago. So now you have this shrinking interior pulling away from a rigid crust that is already set in its size.
So the shell is suddenly too big for the body inside it.
That's a perfect description. I think the best analogy is the grape turning into a raisin.
I was just thinking that.
As the pulp inside the grape dries out and shrinks, the skin suddenly has way too much surface area. It has to go somewhere. It can't dissolve. It can't just disappear. So what does it do? It buckles. It folds over on itself to take up the extra space.
And that folds, that's the ridge.
That is the ridge. In geology, we call this a thrust fault. The crust is being put under immense global compression. It's being squeezed from all sides until the rock literally snaps. One section of the ground is thrust up and over the adjacent section to accommodate the smaller surface area.
That is such a powerful image. The moon is literally crushing its own surface because it's imploding in slow motion.
Imploding might be a bit dramatic for the timescale, but contracting is spot on. It is a global squeeze. And the numbers are pretty impressive. Scientists estimate the moon has shrunk by about 150 feet, roughly 50 meters in radius over the last several hundred million years.
150 feet. That doesn't sound like a lot for a body the size of the moon.
It sounds small, but think about the energy required to compress a solid ball of rock that's over 2,000 miles in diameter by 150 feet. That is a tremendous amount of stored stress energy that has to be released, and it releases it by breaking the rock,
which creates these faults. Now, the study makes a distinction here that I want to clarify. We're talking about SMR's small mare ridges. But you mentioned earlier that we already knew about ridges in the highlands. The study calls those lobate scarps. Is there a real difference, or is this just scientists loving different names for the same thing?
It's a great question. It's a distinction in geography, mostly, but not really in mechanism.
Break that down for me.
So, lobate scarps are found in the highlands, the ancient, rocky, mountainous terrain. We've known about those since the Apollo missions. We've seen them. We've mapped them. They look like big stair steps or cliffs in the landscape.
Okay, so they're the highland version.
Exactly. And SMRs are essentially the same type of feature. They're just found in the Maria, the basalt lava plains.
Okay, so it's just about where they are located. It's like calling a sandwich a sub in one city and a huggy in another. It's the same thing.
That's a fair analogy. And the key finding from this analysis by Knuppever and Waters is that it confirms they are formed by the exact same type of faults. They are both thrust faults. They are caused by the exact same global contractional forces.
It's the same squeeze, just happening in different types of rock.
It is. And here is the smoking gun, the real clincher. The study found instances where a lobate scarp in the mountains travels down a slope, hits the flat mare, and transitions directly into an SMR.
Oh, wow. So it's one continuous crack running from the mountains right into the sea, so to speak.
Exactly. It's a single fault system that completely ignores the terrain boundary. And this is powerful evidence because it confirms that the shrinking isn't localized. It's not just something happening in the old mountains, it's a global contraction. The entire moon is tightening its belt.
That answers the what and the why. But I really want to talk about the when. Because, recent in geology usually means like a billion years ago. Scientists have a totally warped sense of time compared to the rest of us. How fresh are these wrinkles?
This is one of the most exciting parts of the study for me, the dating.
Okay, so how do you date a wrinkle on the moon without actually landing on it and taking a rock sample? We don't have carbon dating for rocks from orbit.
No, we don't. We use a clever technique called crater counting. It's one of the most fundamental tools in planetary science.
Right. Walk us through that logic.
It's based on probability and a classic geological principle, the law of superposition. The moon, like anybody in the solar system, is constantly being bombarded by meteoroids. Big ones, small ones, tiny micrometeoroids. Over billions of years, surfaces accumulate craters like a sidewalk accumulates gum.
Gross, but a very effective image.
A very old surface, like the highlands, will be absolutely covered in craters. It's saturated. You can't make a new crater without destroying an old one. A brand new surface, like a fresh lava flow, will be smooth and almost pristine.
Okay. More pock marks equals older skin. That makes sense.
Exactly. Now, you look at the relationship between the ridge and the craters around it. If you have a ridge, an SMR, and it cuts through a small crater, distorting it or breaking it in half, what does that tell you?
It tells you the ridge formed after the crater. The ridge is younger.
Precisely. But if there are tiny, fresh-looking craters sitting on top of the ridge, and they are undisturbed, perfectly round little bowls, then the ridge must have formed before those craters hit.
It's a game of geological layering. Who is on top of whom?
It is. And by carefully counting the density and size of craters on and around these ridges and plugging that into models of how often craters of a certain size form, the team was able to calculate an average model age. And the numbers are, they're shocking.
Okay, hit me with the numbers.
The average age of these small mare ridges is roughly 124 million years.
124 million.
And for comparison, the lobate scarps in the highlands, which Tom Waters had previously analyzed, have a similar average age of about 105 million years.
Okay, I need you to contextualize this for me. To me, a human who hopes to live to maybe 90, 124 million years sounds incredibly ancient. That's the Cretaceous period on Earth. Dinosaurs were walking around.
It feels like an eternity to us. But you have to shift your perspective to geological time, to cosmic time. The moon is about 4.5 billion years old.
Right, so 4,500 million years.
Exactly. So if you imagine the moon's entire life as a 24-hour clock, from its formation at midnight to the present day, 100 million years is the last half hour, maybe even less. It's the last few minutes before the clock strikes now.
Oh, wow. Okay, that puts it in perspective.
These features represent the last, 2 or 3% of the moon's entire history. In geological terms, these are fresh wounds. They are very likely the youngest tectonic features on the entire lunar body.
So when we look at the moon, we aren't just seeing ancient scars from its violent birth. We aren't just seeing the bombardment from the early solar system. We are seeing things that happened, well, yesterday, in space terms.
And the really big implication of that youth is that the process is likely still forming them.
That's the kicker, isn't it? An average age of 100 million years doesn't mean they all formed and then stopped 100 million years ago. It means the process that made them has been active in the very recent past and is, in all probability, ongoing.
The moon is still cooling. We know that from thermal models. Therefore, it is still shrinking. Therefore, the stress is still building up in the crust. Therefore, the crust is still cracking.
Right. Which brings us to the part of the conversation that sounds a bit like a disaster movie. If the crust is snapping to make these ridges, that snap must release a lot of energy. When rock breaks under that much pressure, it's not quiet.
It creates seismic activity.
Moonquakes.
Moonquakes, absolutely.
We've all heard of earthquakes. We know about the devastation they can cause here. But moonquakes are a real documented phenomenon.
Oh, they are very real. The Apollo astronauts actually placed seismometers on the lunar surface. Apollo 11, 12, 14, 15, and 16 all left working instruments behind. They formed a network.
I remember seeing pictures of those.
And they recorded thousands of seismic events between 1969 and 1977 when they were finally turned off to save money.
And this new study connects those recorded quakes to these ridges.
It solidifies the connection, yes. There are different types of moonquakes. Some are very deep, caused by the tidal pull of Earth's gravity. But the shallow ones, the ones that happen in the upper crust, those are the dangerous ones.
And those are the tectonic ones.
Those are the tectonic ones. And Tom Waters, one of the authors of this new study, had previously done work that linked the lobate scarps in the highlands to some of the strongest shallow moonquakes recorded by the Apollo network. He basically triangulated the epicenters of the quakes to these known faults.
Okay, so we knew the highland scarps were seismically active. But now we have this new map.
Now we have 11,114 new ridges cataloged in the Maria, which we now know are the same type of feature.
So the safe zone isn't safe.
That is the critical takeaway. Previously, mission planners looked at the Maria and thought, perfect, flat, stable, easy to land on, no cliffs to crash into, no mountains to navigate. But now we know that SMRs are widespread there, and they are formed by the exact same mechanism that causes powerful quakes in the highlands.
So basically, anywhere there is a wrinkle on this new map, there is a potential epicenter for a future moonquake.
That's right. Any place with an SMR has to be considered a potential source of shallow seismic activity. And we just found out they are all over the place, including many of the areas considered prime landing spots.
This really complicates things for the Artemis program.
It complicates things for anyone planning to stay on the moon for longer than a few days, for any kind of permanent or semi-permanent presence.
We are talking about building permanent bases, human habitats, landing pads, mining operations, power stations.
And this is explicitly mentioned in the study. Cole Neipever pointed this out directly. He said, and I'm paraphrasing, that a better understanding of lunar tectonics and seismic activity will directly benefit the safety and scientific success of Artemis and all future missions.
It's moving this whole field from academic curiosity to active risk assessment for human lives.
Think about the engineering challenges. You are building a pressurized habitat. It needs to be perfectly airtight. It's essentially a balloon made of metal or advanced composite material holding a precious, breathable atmosphere against a hard vacuum.
Right. You do not want your balloon to start shaking violently.
You definitely don't. But there's a key difference between earthquakes and moonquakes that makes this even scarier for engineers.
How so? Is the shaking more powerful? A higher magnitude?
Not necessarily the magnitude, it's the duration.
The duration.
The duration. Here on Earth, if a big earthquake hits, it's violent, it's terrifying, but it usually dissipates relatively quickly. Maybe 30 seconds, a minute, maybe 2 minutes of strong shaking. The longest ones might feel like forever, but they are over in a matter of minutes.
Okay, and why is that?
Because Earth is wet. We have oceans, we have groundwater, we have a semi-molten mantle. All that liquid, that fluid material, absorbs and dampens the seismic energy. It acts like a giant shock absorber or a layer of soundproofing.
It deadens the vibration.
It deadens it very effectively. The moon, on the other hand, is bone dry. It's rigid. It's cold, brittle rock all the way down. So when a quake hits, that seismic energy has nowhere to go. There's nothing to absorb it. It just bounces around inside the crust, reflecting off the surface and the interior layers over and over again.
The moon, it rings.
It rings like a bell or a gong. The Apollo seismic data showed that shallow moonquakes, the kind caused by these thrust faults, can last for hours.
Hours? You're not serious?
I'm completely serious. High-frequency shaking continuing for an hour or more is not out of the question for a significant event. Imagine a magnitude 5 quake that just keeps going and going and going.
That is an absolute nightmare scenario. Imagine you're in a lunar base. It's the pitch black of a 2-week-long lunar night, and the ground starts vibrating and just doesn't stop.
It creates massive issues for structural fatigue. Any material, no matter how strong, will degrade when you vibrate it for that long. Seals can fail. Microfractures can grow into critical failures.
What about the dust? I know that lunar dust is supposed to be incredibly sharp and nasty, like tiny shards of glass.
Oh, absolutely. The regolith is a huge problem already because it's so abrasive and it sticks to everything electrostatically. If you shake the ground vigorously for an hour, you are mobilizing that dust. You could create a persistent low-gravity dust cloud that could coat solar panels, rendering them useless, or jam airlocks in moving parts.
It really changes the real estate value of the Maria, doesn't it?
Yeah.
You can't just pick a flat spot anymore. You have to pull up this new tectonic map first.
You have to. You have to identify the SMRs and give them a very wide berth. You do not want to build your billion-dollar habitat on top of a fault line that is actively engaging in crustal compression.
It's wild to think about. We always worry about the big, obvious space dangers, radiation, or lack of air, or the extreme cold, but we rarely discuss the ground itself opening up, or rather, shifting violently beneath our feet.
It adds a whole new layer of due diligence to the site selection process that is absolutely critical. We need to define seismic exclusion zones around these features.
So looking at this study as a whole, what it really provides is a catalog. It's a comprehensive map of these danger zones.
It is a comprehensive catalog of global contractional features, yes. It's a foundational piece of work.
And it was all done using data from the LROC, is that right?
That's right, the Lunar Reconnaissance Orbiter Camera. LRO has been circling the moon since 2009, taking these incredible high-resolution images. It's mapped the moon in better detail than we have mapped some parts of the ocean floor right here on Earth.
I just want to take a moment to appreciate the sheer grunt work involved here. These researchers, Nieperver and Waters and their team, didn't just push a button and have an AI find these things. They manually mapped over 2,000 of these tiny ridges.
It is meticulous, painstaking work. It requires a highly trained eye. You have to be able to look at these images, often with different lighting conditions, and distinguish a subtle tectonic ridge from a crater rim or a lava tube collapse or some other feature. It's a monumental effort.
But that labor is what completes the global picture. That seems to be the consensus here. We aren't just looking at isolated oddities in the highlands anymore. We are seeing a single, unified planetary process.
That's the key. The moon is cooling, the moon is contracting, and as a result, the crust is breaking. And it is happening everywhere, highlands and Maria alike.
It's foundational science. You know, it's the kind of work that doesn't always make the front page of the newspaper because it's not a flashy explosion or a discovery of a new alien, but it's the work that keeps future astronauts alive.
It's the safety manual. You can't write the safety manual for a new territory until you understand the hazards. The study is a critical chapter in that manual.
As we wrap up this discussion, I have to say my view of the moon has definitely shifted. I think for a lot of our listeners, it probably has too.
In what way has it shifted for you?
Well, like we said at the start, I looked at it as a nightlight, a beautiful but ultimately static object. Magnificent desolation, as Buzz Aldrin so famously called it. But desolation implies that nothing is happening. It implies stillness.
And that's the great misconception we're overturning.
It is. Now, when I look up at it, I'm going to think about that cooling process. I'm going to picture that interior shrinking and the crust buckling under the strain. It's like the moon is still settling into its old age. It's shivering.
That's a beautiful, if slightly unsettling way to put it. It is shivering, it is shrinking, it is cooling, and it is quaking. It is a body trying to find a comfortable, stable position as it loses its primordial internal warmth.
We've really moved from looking at the moon as a fossil to looking at it as a dynamic world with its own internal life. It might be a very slow life compared to Earth's frantic tectonic shifting, but it's there. The pulse is there.
And we're just beginning to understand it. The more we look and the better our instruments get, the more we find it's still a world of secrets.
Here's the thought to leave you with, and it's been on my mind through this whole conversation. We talk so much about becoming a multiplanetary species, about colonizing space. We talk about terraforming, about bending these other worlds to our will. But this study is such a humble reminder that we don't control these worlds.
No, we certainly do not. We are guests at best.
The moon doesn't care about our landing schedules or our habitat designs. It's going to keep shrinking, and it's going to keep shaking whether we are there or not.
Geology always wins in the end. It operates on timescales we can barely comprehend.
So if we are serious about planning to live there, we have to answer a very, very difficult question. How do we engineer buildings and infrastructure for a world that is slowly, inexorably crushing itself?
That is the engineering challenge of the century for lunar exploration.
The ground beneath the feet of future astronauts is simply not as solid as we once thought. It just makes you realize that even on a dead rock, nature is still very much in charge.
Indeed it is. A powerful reminder.
Thank you so much for joining us on this exploration of lunar tectonics. It's been a fascinating look at the hidden and very active life of our nearest neighbor.
It really has. My pleasure.
Keep looking up.
Take care.